All right. Hello. Welcome back to chapter 4, part 2. This is slide 16, and we're going to dive right into talking about actual, theoretical, and percent yields. Okay, so the theoretical yield is the maximum mass of a product that can be obtained from a when a reaction is determined by the limiting reactant. Okay. So let's take a look at some important terms here. A percentage or percent yield is the ratio of the actual yield to the theoretical yield, and it measures your reaction efficiency. In engineering or manufacturing, this is really quite important because this basically determines how much product you make and how much product is lost. Okay. Our theoretical yield is the quantity determined from stoichiometry. It's the maximum mass that we could make. Okay. But you really never make the maximum amount. You just don't. I mean, it would be nice if you could, but it doesn't work like that. There's almost always some kind of waste. So that brings us to this important term here called an actual yield. This is the actual amount that actually can be made in a laboratory or factory, minus the waste or the inefficiency involved. Now, our percent yield here or percent yield is equal to the actual yield or over the theoretical yield. So let's call this is uh let's see, sorry. Hang on. I wanted to use a different symbols there. There we go. Okay. So I'll usually identify this as percent yield like this. And actual yield we'll call AY, and theoretical yield we'll call TY. And then because it's a percent, we have this 100 here. So like if you're like me and you really like proportions instead of equations, you can set this up as your percent yield over 100 equals your actual yield over your theoretical yield. And for some people, it helps to set up your equations in a proportion form and then cross multiply rather than think about, well, where does this variable go? Where does this variable go? So that's my little favorite there. All right, here we go. Now we are into, of course, some yield practice. And this is slide 17. Okay. And it says that in a laboratory experiment, a student heats 42.0 grams of our NaHCO3. Okay. So just as a little help here, this is a sodium bicarbonate. And sodium bicarbonate is also baking soda. All right. Now we know from our work before that we're going to need a molar mass for this. And for this sodium bicarb, our molar mass is 84.006 grams per mole. Okay. And what we want to know here is it says we determine that 22.3 grams of sodium carbonate is formed. Okay, so what this means is that this 22.3 grams is our actual yield because this is what we make. And we're going to need a molar mass of that. And the molar mass of our sodium carbonate is 105.988 grams per mole. Okay. So now some steps here that I've got built in. Our step one is to use stoichiometry to calculate the theoretical yield of our product here. All right, so let's go ahead and set that up. So we start with our given. We have 42.0 grams of our sodium bicarbonate. And then stoichiometry, so we need our molar mass. So on the bottom, we have our 84.006 grams of sodium bicarbonate per mole. And then the next thing that we always use is our molar mass. And we have 2 moles of our sodium bicarb and an understood 1 here. So we put 2 on the bottom. And we put the 1 that goes with our product on the top, Na2CO3, sodium carbonate. And then the last thing that we need here is our molar mass, 105.988 grams of sodium carbonate per 1 mole of sodium carbonate. Okay. And that means that our theoretical yield is 26.5 grams of Na2CO3. And this is our TY, our theoretical yield. Now, our step 2 here is to calculate our percent yield. And so using the equation from before, our percent yield is equal to our actual yield. That's what we actually made, or 22.3 grams, divided by our theoretical yield, 26.5 grams, and times 100, which turns this with 3 significant figures into 84.2% efficient. Okay. So those are kind of that 2 steps. And most problems are going to be 2-step problems. So let's take a look at another one. So this is slide 19. Okay, so here we have, it says how many grams of KClO3, so this is going to be our unknown, okay, are needed to produce 42 grams of, oh, I'm sorry, I was just looking at the wrong one, not slide 19, slide 18, at least I got that more quickly. All right, and our needed to produce 42 grams of, I need to take a look at this. Oh, we're not making KCl, we're making oxygen, O2. I'm looking at my sheet now. Okay. And so we have 42.0 grams of O2. And this is, we need to produce this. So this again is our actual yield. Okay, so the steps for this are going to be a little bit different from the steps before, but we're still going to need a molar mass. So the molar mass here for our unknown is 122.54 grams per mole. Always a good idea to calculate those ahead of time so that it's easy to plug things in. And for our oxygen, again, you might have this one memorized by now, but 31.998 grams per mole for our oxygen. Okay. So now what it's doing is we're calculating our theoretical yield. So let's take a look at that. So we have percent yield over 100 is equal to actual yield over theoretical yield. So this is what I love about proportions, is because I find that they're so easy. So if I'm solving for theoretical yield, then what I'm going to do is I'm going to cross multiply like this. And this means that my theoretical yield is equal to my actual yield times 100 divided by my percent yield. Okay, there we go. Okay, so my actual yield is 42 times 100 divided by 65. And I always just kind of leave off extra zeros here because it just makes the calculations easy. I know I can have 3 significant figures. Okay. And so what this means then is that I have 64.6 grams of O2, and that's what I need to aim for. That's my theoretical yield. If I aim for my actual yield, I won't make enough because I'm only 65% efficient. So now I'm going to use that value, that 64.6 as the starting quantity we're going to use 64.6 as my given, okay, to find my starting quantity. So now I start with that 64.6 grams of oxygen. And now I go right through my stoichiometry again. 31.998 grams of O2 per mole. And now I need my mole ratio, and that is 3 moles of O2 on the bottom to 2 moles of KClO3, potassium chlorate. Okay, just as a little reminder there, KClO3 is potassium chlorate. Okay. And every 1 mole of KClO3 has a mass of 122.54 grams. Excellent. Okay. So here we have 64.6 times 2 times 122.54 divided by 31.998 and divided by 3, which will give me a final answer of 165 grams of potassium chloride, KClO3. Okay. And there's my final answer. So this one is just basically working backwards from the problem that we had in our previous slide. All right, let's do another problem. Excuse me. All right, so now we're up to slide 19. And we're looking at solution stoichiometry. Now, solution stoichiometry combines moles and molarity and volume in a slightly different way than our usual stoichiometry. So let's go ahead and take a look at that. First, you notice here that you have 750 milliliters of a 0.806 molar sodium hypochlorite. ClO with a 1- charge is hypochlorite. Okay, so first of all, what this means, this 0.806 means that we have 0.806 moles per liter. That's what the molarity means. That I have to convert my milliliters. Okay, so this 750 milliliters becomes, we have 750 just to review how this is done, and there are 1,000 milliliters in a liter, and that means that we have 0.7500 liters of our sodium hypochlorite. And they want to know, they tell us that we have excess ammonia. So I can just kind of put that in there so that we know that we're ignoring it. And then it asks how many moles of hydrazine. Okay, so this is our unknown. So when we're working through these stoichiometries, the trick is knowing where to stop. And so here we have 0.7500 liters of our sodium chloride. So that's what we're going to start with. We're going to start with our volume in liters. And I'll go ahead through at the end and write this out. All right. The next thing that we need, no, I'm going to go ahead and do it now, actually. Okay. So we start with our volume in liters. Okay, and the next thing that we need is our molarity, 0.806 moles per 1 liter. So this is our molarity. The next thing, oh, and I'm going to go ahead and sneak in that NaClO here, and NaClO, that should have been in there as well. Okay, now what we need is a mole ratio. And you can see from this, there's an understood 1 there. So we have 1 mole of our sodium hypochlorite. And in this case, we only have 1 mole as well of our hydrazine. So this becomes 1 mole of N2H4. And now notice that they're only looking for moles, not grams. So that means that's where we end. We don't care how many grams because this is an aqueous solution. All we are going to care about is our concentration, and we don't need grams for that. So because we're looking for moles, we can end with moles here. Okay, so this last piece is our mole ratio. And this gives us an answer of, we have four significant figure, actually only three significant figures. Okay. But since we're continuing on, usually what I will do is I will go one extra sig fig at the beginning of the problem to make sure that my final answer is a little bit more accurate. So we have 0.6045 moles of my hydrazine, N2H4. All right, so now our second piece here is saying if the final volume of the resulting solution is 1.25 liters, what will be the molarity of the hydrazine? Okay, so with this, I'm going to remember this equation from chapter 3 that molarity is equal to moles over my volume in liters, or my liters of solution. So I have that 0.6045, and I'm going to put it over the 1.25 liters. And that will give me a final hydrazine molarity of 0.484 molar. And I'm right back to my three significant figures that I started with. All right. Okay, so this is sort of an introduction to titration. Here we have slide 20. Okay, now let's just take a look at what's going on here. So in this first one, we have a burette. So right there, this is a burette, this tall piece of glassware. And down here, we have a beaker or an Erlenmeyer flask. We use beakers in our lab, but you can also use Erlenmeyer flasks. We usually use a beaker because we're also using a pH probe, and both of them don't fit into an Erlenmeyer flask. So down below, usually in your beaker or your flask, you have hydrochloric acid. In your burette on the top, you have sodium hydroxide. And when they combine perfectly at our end point, so when we're completely neutral, we are at our equivalence point or our end point. And if we have an indicator in it, like phenolphthalein, it'll be pink. Okay, so remember from our balanced equations, this means we don't have either sodium hydroxide or hydrochloric acid left. We just have water and some kind of an ionic compound. So let's go ahead and practice this. So here we are on slide 21. And we'll take a look at some balanced equations and titration practice. So first of all, this tells me that we have sodium hydroxide and sulfuric acid. So we have to start with a balanced equation. So we start out with that NaOH, and it's aqueous. And we're adding in our H2SO4, and that one is also aqueous. And we're always going to be yielding water. We know that from last chapter. And our sodium sulfate, Na2SO4, and aqueous. And the reason for that, remember, is that we have sodium ions and sulfate ions, okay? All right, so now our next part to that is that we have to balance it. And we know that we need, for every one hydrogen, we need one hydroxide. So if we have two hydrogens here, then we need two hydroxides. And so we'll put a 2 there and a 1 there. And two hydroxides and two hydrogens will give us two waters. And we'll have one of our sodium sulfates left over. Okay, very important. We have to start there. Okay, now it tells me that I have 24.75 milliliters of my sodium hydroxide. And again, from the previous slide, I know that I need to convert that to 0.02475 liters. And my sodium hydroxide is 0.503 molar. Okay, and now I have my sulfuric acid over here. And my sulfuric acid, well, it says that the problem tells me that I have a 15 milliliter sample of my sulfuric acid, which I know from my previous slide of conversions gets me to 0.015 liters. Okay. And so I only have two significant figures here. No, sorry, there were four here. 1, 2, 3, 4. So we have four significant figures. And I want to know basically what the concentration of this is. So that's going to be the unknown there. So now I have these two steps. So stoichiometry step number 1 is to use the stoichiometry to find the moles of the unknown. So remember, we start that one with our volume in liters, and that's 0.2475 liters of NaOH. Okay, so that's the volume of my given in liters, of course. And now the next thing that I need there is my molarity of my given, and that's going to be 0.503. And remember, molar means moles per liter. Okay, and that's what allows us to cancel out those liters. All right, now in the next piece, we need a mole ratio. And hang on, I forgot a very important thing again, and that is to include all of my units. That's mole sodium hydroxide per liter. Sodium hydroxide, there we go. And then my mole ratio is going to be a 2 moles of NaOH on the bottom and 1 mole of sulfuric acid on the top. Okay. Now I have 0.2475 times 0.503 divided by 2, which gives me 0.006225 moles of my unknown, my H2SO4. Okay. And now here at the bottom, I have calculate M. So again, calculating molarity. Molarity is moles per volume in liters. Okay, so that means I've got my moles here, 0.00625 moles, and it's divided by the volume of in liters that I have right here. So 0.015. And I can have 4 significant figures from my originals in there. Oh, actually, look at this. For my final answer, I can only have 3 significant figures. So in my final answer, this will become 0.415 molar, and it's H2SO4. Okay. Let's try another one that's going to look just like this. And here we have slide 22. Okay. All right. Now, here we go. We have again, always, we have to start with that balanced equation. And so now we see that we have potassium hydroxide, so very similar, plus our H2SO4 yields water and K2SO4. And again, if you don't remember how to do that, you probably need to spend a little bit more time on your chapter 3 before the chapter 3-4 exam. All right, and then we will balance this, and it's basically the same balancing that we had before. All right, so now let's take a look at what we have where. All right, so here we have 23.74 milliliters of 0.5 molar potassium hydroxide. Okay, so this one becomes 23.74 milliliters. And from before, we know that this converts automatically to 0.02374 liters. And we have 0.5 molar or moles per liter. Okay. Now over on the other side here, we have our H2SO4 and we have 25 milliliters of our H2SO4, which converts to 0.025 liters. And we're looking for the concentration. So this is the same process that we had before. Again, we start with a volume of our given, and that is 0.2374 liters of KOH. And the next thing that we will have is we'll have our molarity. And our molarity for our KOH is 0.5 moles of KOH per liter. And the last thing that we need here is a mole ratio. And we have 2 moles of potassium hydroxide, KOH, for every 1 mole of sulfuric acid, H2SO4. I'm only going, actually, as I look at this, I'm going to only be able to have 3 significant figures in the end, but I always like to leave one extra one when I have this intermediate step. And so this would give me 0.005935 moles of H2SO4. And again, here I calculate molarity equal to moles per liter. And so that gets me 0.005935 moles for every, in right here, this one. So in 0.025 liters of solution. And now I can have 3 significant figures for my final answer, and I get 0.237. And again, that's molarity or molar H2SO4. All right, so those 2 problems were almost identical. Hopefully that gives you a really good idea of how to do this. Okay, now we just have 2 more slides, and then we'll be done with this chapter. Okay, so first of all, we have slide 23. Okay, and this is more practice. It's a percent yield problem. Okay, so let's go ahead and begin, as always, with balancing our equations. So here I have Na2. So I'm going to go ahead and put a 2 here so that I have 2 sodiums right there. Okay, and now I have 1 carbon here, and so that matches there. So go ahead and put a 1 there because I'm probably going to keep, so I've got 2 times carbon, so that gives me 1 carbon there and 1 carbon here. So 1 and 1 gets me that 2 carbons that are here. Okay, and now I'm going to take a look at this. Now I have 2 hydrogens here and I have 2 hydrogens here. So I'm going to go ahead and put a 1 there and see now if that works out for everything. So here I have 3 oxygens and I have 2 oxygens and I have 1 oxygen, which gets me 6 oxygens. And here 2 times 3, I have 3 and 3. I have 6 oxygens on the other side as well. All right. Excellent. So the balancing is complete. And I'm just going to erase my extra stuff so that I can get through that. Okay. And now it says down here to calculate our theoretical yield, okay, because this is using the reaction. Two sodium bicarbs yields 1 sodium carbonate, 1 carbon dioxide, and 1 water. And we want to know how many grams of our sodium bicarbonate, okay, so grams, are needed. So that's my unknown. are needed to produce 65 grams of sodium carbonate. Oh, sorry, I don't know why this isn't adding. This should read, it's on your sheet, I believe. So, sodium carbonate. If our reaction, I don't know why it's not on the slide. Hopefully it's for you, but let me finish it out here. If our reaction has an 84.15% yield. That's the rest of the problem, if for some reason it's not printed for you either. Okay, so this tells me that we have 65.0 grams of our sodium carbonate, and this is our actual yield. Okay, so this is very similar to what we had before. Notice here that it says to calculate our theoretical yield, okay? And remember that we have AY over TY is equal to percent yield over 100. And if I'm going to plug that in, then I get 65. Now, hang on. Let me go ahead and show you how to do that cross multiplication again. So we cross multiply to solve for TY by drawing this line like that. And that then will give us theoretical yield equal to actual yield times percent. Sorry, goodness, I keep saying and writing the wrong thing. Okay, actual yield times 100 divided by percent yield. Okay, so we calculate our theoretical yield by taking our actual yield, which is 65 grams, times 100, divided by my percent yield, 84.15. And that beginning here gets me a 77.2 grams of sodium carbonate. Okay, and this is my theoretical yield, and it becomes my given for the next step. Okay, so I start my stoichiometry now with that value, 77.2 grams of Na2CO3. And the next thing that I'm going to need is my molar mass. Oh dear, you know what? I'm going to take a moment and I'm going to calculate out some molar masses real quick and place those up here. The sodium, the Na2CO3 has a molar mass of 105.988 grams per mole. And my sodium bicarbonate has a molar mass of 84.005 grams per mole. All right, so now I have those to begin with. And so here I can place my 105.988 grams of Na2CO3 on the bottom for 1 mole Na2CO3. And the next thing that I need here is a mole ratio. And for every 1 mole of sodium carbonate, Na2CO3, I have 2 moles of sodium bicarbonate, NaHCO3. And the last piece that I need here is my molar mass, which tells me that 1 mole of NaHCO3 goes with 2 moles of, sorry, that is not correct. Goes with my molar mass, which is 84.005 grams of NaHCO3. And when I calculate those out, and I can have 3 significant figures, that gives me 122 grams of sodium bicarbonate. and that is how much I need to start with in order to make 65 grams of sodium carbonate at an 84.15% reaction yield. Okay, one final practice slide. And here we have slide 24. And in this practice problem, this is a titration practice problem. It's a little bit different from what we've done before. And here it says, let me make sure. Oh, good. This one's all written down. It says how many milliliters of a 1.25 molar hydrochloric acid. Okay, so let's stop there for a minute. So we have 1.25, and molar means moles per liter of my HCl. And I'm looking for volume, so that's going to be my unknown. Okay. And then over here, see, it says 2.785 grams of solid, I'm just looking at the word, solid calcium hydroxide here. Okay, so I can put that right here, and I'll notice that's my given then, 2.785 grams. So because I have that mass in there, that means that in this case, I'm going to need a molar mass, and the molar mass for my calcium hydroxide is 74.092 grams per mole. All right, so let's go ahead and do our step one, which is to use our stoichiometry to find the moles of our unknowns. So we're going to be stopping early. So we have 2.785 grams of our calcium hydroxide times, now again, this is where that molar mass goes, the 74.092 grams of calcium hydroxide on the bottom, per 1 mole of calcium hydroxide on the top. And then the next thing that we need is our mole ratio. Oh, look at that. I forgot to balance it first. Total rookie mistake. Okay, so now in this one, see how we have 2 hydroxides? That means that we're going to need 2 of our hydrogens. 2 hydrogens and 2 hydroxides make 2 waters. And now I'm going to go ahead and check it. 1 calcium, and 2 chlorides and 2 chlorides means that this one will be a 1, and so will this one. All right, great. Now I have a balanced equation, and I can place in here that I have 1 mole of my calcium hydroxide there on the bottom, and 2 moles of my hydrochloric acid on the top. Okay. And stopping here, so I'm looking for moles of my unknown, gives me, because I'm looking for moles unknown. So if that's the case right here, then that's why you stop with the mole ratio, is because you don't want grams, because we're looking for concentration. Okay, so that gives me 0.07518, and that's moles of HCl. Now I need to solve for volume. Okay, so if molarity is equal to moles per volume, okay, then that means that volume is equal to moles over molarity. All right, so how are we going to do this? So this means that we have our moles, so that's 0.7518 over our molarity. Now, molarity means 1.25, and that's moles on top, sorry, over and moles per liter. So that cancels out our moles per liter, and it will give me a value of 0.0601 liters, 1, 2, 3 sig figs. But we can't measure 0.0601 liters. So that means that we need to convert that to 60.1 milliliters. And the way that I did that is to take 0.0601 liters and 1 liter on the bottom and 1,000 milliliters on the top, like that, for our conversion. And that will get me 60.1. Excellent. That concludes this chapter, and I will see you in class.